I'm going to start the next lecture, and in this lecture we are going to discuss a new method for finding the solution of the system of linear differential equations. We already discussed two methods. One was given by elimination and second was by Cramer rule. And in both methods we try to eliminate one of the variable and to write the system, from the system we write a differential equation. So here in this one, this is different from these two. So we use the linear algebra, which we have studied already in this one also, and we're having system of equations given to us. We write in the form of ax equal to b. B is the constants and a is a coefficient, x is the unknown. Similar to this one, I take the example which I have already discussed for the homogeneous system before, and I take this one. This is my example. You have dx by dt plus x plus 3y equal to 0 and x plus dy by dt minus y equal to 0. Now we rewrite this one and we take dx by dt and dy by dt on the left hand side and all other values on the right hand side. So we get here dx by dt is equal to minus x minus 3y and dy by dt is minus x plus y. So minus x minus y and minus x plus y, we just use this method of the matrix multiplication, and we say we can write in a matrix form. So one matrix becomes the column matrix dx y dt and dy by dt equal to, this become here the coefficient is minus 1, minus 3, minus 1 and 1. And unknowns are x and y, so we have multiplied by unknown. So we rewrite this one and we say we can take d by dt outside the vector and get a dx by dt of xy. Now this x is my unknown vector, that's give me the solution. That's my x and y, this is my vector. So I can write x this way as dx by dt is equal to minus 1, minus 3, minus 1, 1. xy and xy is my x. So I can write equation 1 as x dash is equal to ax. So this is my standard equation which I will be going to discuss with you, and using this one I will draw certain results. So this is the case when we are having homogeneous differential equation. Now I give you another example how we rewrite this one when we have non-homogeneous differential equation. So we're going to discuss an example where I'm going to take the non-homogeneous differential equation and we'll check it how we can write in the form of a matrix. So here we are having dx by dt is equal to x plus y minus 2z plus 3t. dy by dt is 2x minus y minus 3z plus 4e to power t square plus t, and dz by dt is equal to x plus y plus z plus et. Now this dx by dt, we have in the right hand side, keep it like this. We have dx by dt and write in a matrix form. This is dy by dt, and here we have dz by dt. This is my matrix. And then I have two parts of this matrix. One is the matrix which is having the variables. This is my x plus y minus z. We have 2x minus y minus 3z. Having x plus y plus z. And then I'm having the function of t. They are not function of x and y. So this is 3t and 4t square plus t and e to power t. Now I rewrite the equation. Here I can take d by dt out and say this by d by dt of the vector x, y and z. And on my right hand side I can write here this as I did in the case of system of linear equation. I write ax. Similarly I'm going to write the same thing. A are the coefficient. Our coefficient are 1, 1 and minus 1. We have 2, minus 1 and minus 3. We have 1, 1 and 1. And here I get here x and y, x, y and z. This is my vector. And then I have here the values, the function of t, that is 3t, my dependent variable plus t, independent variable plus e to power t. So if I write a general form, that this is my x is my vector x, y, z, vector of unknown. So I can write this one as this is my d by dt of x plus I write here ax, and plus I write this one as f of t. This is my right here f of t, and now I can write here this is my x dash. My differential equation is ax plus f of t. Because of this function f of t, if it is 0, this is homogeneous, and if it's non-zero, this is non-homogeneous. So similar to that one, if you want to find the solution of this one, so here this one will be xc plus xp. We find the homogeneous part of the function and we take the solution of that one, and then we solve for the non-homogeneous part. As we are doing for undetermined coefficient or things like that, when we apply the same one to find the solution for the system of linear equation. So we are going to discuss another example where we are going to use the non-homogeneous differential equation. I have here a system of differential equation dx by dt is equal to x plus y minus z plus 3t and dy by dt is equal to 2x minus y minus 3z plus 4t square plus t, and if dz by dt is equal to x plus y plus z minus e to power t. So we make group of that one, then we are having the derivatives, then as we are having the system of linear equation, we are having the coefficient, and then those which are not containing x, y and z. So we get here three groups. One is the matrix dx by dt, dy by dt, dz by dt, and the other is our equation which are not containing right hand side, which is not containing the function of t. So get x plus y minus z, 2x minus y minus 3z, and x plus y plus z. And I am having here the last column matrix is our 3t, 4t square plus t and e to power t. Further we take here this d by dt out, and then we write this equation in the form of the matrix form, again multiple of x, multiplication of the solution vector and the coefficients, we get 1, 1 minus 1, 2 minus 1 minus 3, 1, 1, 1, and then we are having x, y and z. So plus we are having the column matrix. So this we say our x, y, z is our vector, solution vector. So we can write here this is a vector of unknown, we can say dx by dt is equal to ax plus ft. We take a is a matrix of the coefficient, x is matrix of unknown, ft's are the function of t. They are not containing x, y and z. So we can write here x dash is equal to ax plus f of t. When we want to solve it, as you know, we are having non-homogeneous system, then we are having the two parts of solution. One is the homogeneous part and then a particle solution. So we get here x equal to xc plus xf. So we first find the homogeneous part, then we find the f of t. Now we have discussed the methods. Two methods we have discussed. One is by elimination and other is by using Cramer rule. Thus we have given you the example for all the two methods, many examples. Now we are going to discuss a new method, and that is our eigenvalue, eigenvector method. So first I explained you what's mean by eigenvalue and eigenvector. Eigenvalues are related with the matrix. So we just take a matrix and we take a minus lambda I, and we find determinant of that one, and we solve in lambda, we get the characteristic equation and solve it, and then we find the root of that one, and the roots, the values which we get there are known as eigenvalues. For example, here we are having x dash is equal to a x, and when we make the solution, we know the solution of this one is always we say small x. When we're taking x and y, then x is equal to e to power mt, y is equal to e to power mt, and here we say the vector is x. We say take a vector k is with the column matrix with k with the two values k1 and k2, and e to power lambda t. So when I take derivative of this one, then I get dx by dt is equal to k e to power lambda time e to power lambda t, because derivative of e to power lambda t is e to power lambda t, and then derivative of lambda t is lambda. So I substitute here, I get here the value of x dash is k lambda e to power lambda t is equal to a k e to power lambda t. So e to power lambda t we cancel from both the sides because that's not equal to 0. We get here k lambda is equal to a k. I rewrite this one, I get a k is equal to lambda k. Now in this equation, when we take this equation, then in equation is very important. So in this equation I just explained you. In this equation we are having here this a, this our operator. This operates upon k and give me the lambda k. So k is my eigenvector and lambda is my eigenvalue. So when you solve this one equation, then we get here the lambda, the eigenvalues, and also the eigenvectors. So here we are having the example, we just rewrite that one. We take this one to the left hand side, I get k minus lambda k, or I take k common, I get a minus lambda k equal to 0. Lambda is a scalar, but this is a vector equation. We can't add a scalar to a vector, to matrix. So we make it a matrix. Our A is 2 by 2 matrix. So our K is with K we multiply with lambda we multiply by I is also 2 by 2 matrix. If K was 3 by 3 matrix, then I was 3 by 3 matrix. So we are having this equation A minus lambda K I equal to K. This equation have both type of solution, because here K is our K1 and K2, the two unknowns we are having here. When we solve it, we get the value of K1 and K2. There are two possibilities homogeneous equation. One is that we get here the homogeneous solution. Now they have the trivial solution, the value is 0, 0. But we are not interested in trivial solution, we are interested in non-trivial solution. So then it means we have a condition that determinant of this coefficient must be equal to 0. So having the determinant of a minus lambda k is equal to 0 for the non-trivial solution. So here when we have this equation, we open it, we get here the value, the equation in lambda, and this equation, polynomial equation lambda, is called characteristic equation. We solve it and find the root of characteristic equation. These roots are known as eigenvalues. Then with the eigenvalue, each eigenvalue is a related eigenvector. Then we solve this one by substituting here in this given equation. This is a minus lambda I into k. We find the value of k. This value of k give me the eigenvector. So we are having eigenvalues and eigenvector related to matrix A. So they are related to matrix A. So here we have the solution of the homogeneous equation. Our x is equal to k e to power lambda t. We are having lambda is the eigenvalue, k is eigenvector. So for each eigenvalue we are having one solution. We have x1 is equal to k1 e to power lambda 1 t. For the second value k2, the eigenvalue we are having k small k2 is our k2 is our eigenvector. So x2 is equal to c k2 plus e to power lambda 2. Alright, there is no solution. We are having two solutions x1, x2. They are the linearly independent solution. So we can write the linear combination. We can say our x is equal to c1 x1 plus c2 x2.